Okay, thank you. So my name's Alex, and I'm here today to discuss a fMRI inference method that I've been developing with Professor Thomas Nichols and Dr. Armin Schwartzman over the first 9 months of my PhD. So as a brief overview of what I'm going to go through today, first I'm going to go over current fMRI inference techniques, and in particular, the downfalls of these techniques when applied to large sample data sets. So what I'm talking about here is your UK biobanks and human connectome projects, where we've got thousands of subject data available to us. I'm then going to introduce the contour inference method we've been developing, particularly for application on these large sample data sets. And then I'm going to explore aspects of our method by showing you results we got when applying this method to the HCP and biobank data. Okay, so currently for fMRI inference, we utilize this mask univariate model. So we apply linear regression at each voxel independently to get a statistical parametric map. And then to localize brain function, we threshold this map using null hypothesis testing. So one thing that's quite interesting about this is what we don't compute. So the statistics here have no notion of spatial uncertainty. So what I mean is, if you were to do this study again with different subjects, you would expect these clusters to jiggle about a little bit. But we don't actually compute anything about the uncertainty and spatial precision that we get with this model. Another more fundamental problem with null hypothesis testing is it's been found for studies with large enough statistical power is that it actually finds almost universal activation over the entire brain. And this isn't something crazy. This is known as the fallacy of the null hypothesis. And what I'm presenting on this slide is an example of this happening. So this is a study where they scanned 3 subjects 100 times each. And when they averaged the results across runs for these two multiple comparison correction procedures, they found activation in 80% and 99% of the brain respectively. And on the right-hand side of this slide, I'm showing the percentage of voxels that were active compared to the number of runs. And even at about 35 runs, what we're seeing is over 50% of activation using the family-wise error rate, and almost 90% of activation with the false discovery rate. So we've actually got a real problem on our hands here because we need a little bit more information rather than that there's just activation everywhere. So the perspective that we've come at this is to stop doing a testing procedure and start estimating the parameters you're interested in directly. So how would you do this in a univariate sense? Well, you would get a point estimate of the activation and a confidence interval. And then applying this to the whole brain, you get a cluster and a spatial confidence set. Now, to give us a method that would actually find these clusters, we had to go to a different field of science. So this is some beautiful work that was done by our collaborators, Max Sommerfeld and Armin Schwartzman, where they conceived this contour inference method. And what they were applying it to was geospatial data. So they had 50 years of temperature maps in the United States of America. And here they're trying to infer regions where there is the possibility for global warming. So in particular, they're looking for an increase in temperature of 2 degrees Celsius. And what you're seeing on the right-hand side of this is a figure taken from the paper. And this red confidence set is saying that the southwest parts of America are particularly at risk of climate change. So when we saw this method in action, what we thought is, oh, this is great, because rather than temperature maps, we can apply this directly to fMRI subject data. And rather than inferring on a temperature change, we'd be looking for significant activation in the brain. So, for example, a 1% bald activation. So at this point, you're probably asking, what exactly are the sets that you're seeing here? So I'm just going to use this picture to illustrate, and then we're going to go into contrast later. So when you apply the contour inference method, you get 3 sets. First of all, there's this yellow point estimate set, and this is nested between the red and the blue confidence sets, which are acting kind of like a confidence bound on the spatial precision. So first of all, the yellow set is a point estimate, or the best guess you get from your data of where there's been greater than a 1% bald activation in this study. Then first, the red inner confidence set. For all the voxels in this set, what we're saying is we can infer activation greater than 1% at a 95% confidence level. And then at the same time, we also have this blue outer confidence set. And for this, all the voxels outside this set, so all the gray background voxels in this picture, we would infer have less than 1% activation at the 95% confidence rate. So the blue confidence set here is quite nice because you can never disprove the null hypothesis, but by getting this blue set, we've actually got an upper bound. So for all these gray background voxels, we can infer there has been no significant activation. And when I say 95% here, what I mean is this is simultaneous over the whole brain rather than voxel-wise. So just to give more of an intuition about how this works, I set up this 1D demo. So you can think of this as voxels lying on a line across an axial slice of the brain. So say we have n subjects modeled by signal plus noise models. So here, mu is the mean activation at voxel S, and epsilon is the noise specific to that subject. So averaging your subjects together, you can get this group activation map across all of your locations. So to create the sets that I showed in the previous slide, first the yellow point estimate set. To do this, we just threshold this activation map at the effect size that we're interested in inferring on. So, for example, C equals 1% bald activation. Then to create the red upper confidence set and blue confidence set, we threshold at our effect size, so C equal to 1%, plus or minus some critical value delta. So in doing this, we have these nested confidence clusters, as I showed in the last slide. The real question here is, how can we find this delta so that this holds at a 95% confidence? So in this situation, all of the variability is contained in your noise. So what we do is we estimate the distribution of the noise along the boundary of where your activation is equal to your threshold. So here, where you see activation equal to 1%. Now, we don't actually know what the distribution of the noise is, so the way we get this is by doing a bootstrapping resampling scheme. And then once we've approximated this distribution, we can then find delta directly from it, such that the 95% confidence level holds. So I'm now going to go on and show the results we got when applying this method to first human connectome project data. So here we have 80 subjects, and they were involved in a task fMRI paradigm where they first had to look at scary faces and match them, and then match shapes. And what I'm showing here is the method inferring where a 0.5% bald effect has occurred. So on the left, I'm looking at the faces versus baseline contrast. And what you can see is this nice big red band in the visual cortex where we've got 95% confidence there's been greater than a 0.5% bald activation. And then even nicer, the faces minus shapes contrast, what you see is a tightening of these confidence bands. So not only have we got greater precision in the visual cortex about where this effect has occurred, we've also got these two red dots that have appeared on the amygdalae. So here the method has found activation in the amygdalae. So we then went on to look at this contrast further, but this time we compared inference on a 0.2% bald effect compared to a 0.5% bald effect. And by lowering your threshold, what you find is the red confidence set grows because there's a larger area where we can infer greater than 0.2% bald. And at the same time, your blue confidence set also grows because there's less voxels you can say have no significant activation in this setting. So that was for 80 subjects, but at the start of this talk, I said we wanted to look at data with thousands of subjects available. So to do this, we had to go further than the Human Connectome project and move on to the UK Biobank data. So on this slide, I'm showing the results we got when applying this method to 1,000 subjects and 8,500 subjects for the same contrast from the UK Biobank. So on the left side here, looking at n equals 1,000, what I've done is I've compared the results you get using your traditional inference methods. So on the left-hand side of this figure, what we're seeing is your group activation map thresholded with a family-wise error of 0.05 Bonferroni. And what we do see is there's a slight problem because with this amount of subjects, your group mask gets quite heavily eroded. But at the same time, we still see activation almost over the entire brain. And the color bar on the left here, this isn't deceiving your eyes. You get extremely large t-statistic values. At the same time, the contour inference method what we've had is a real tightening of the sets now. So we've got real precision on the areas of the visual cortex of where this activation has occurred, and at the same time, this activation in the amygdalae. This simply becomes exaggerated in the case of n equals 8,569 here. So for classical inference, you're seeing now even more activation over the entire brain. And then the contour inference method, you've almost got your contour sets on top of each other now. So what we can say here is for almost all voxels in the brain, we can infer where either greater than a 0.2% bald effect has occurred or less than 0.2%. And what's interesting is you'd think with 1,000 subjects, this would be enough statistical power to almost get everywhere in the brain. But what we see in the contour inference maps is when we went up to 8,569, we also found activation in the temporal lobe, which is seen on the left side of the brain. So our next steps for this method are to try and use it for more interesting effect sizes. So here we've just used it percentage bald change, but what we want to go on to do is use this for Cohen's d. So this is percentage bald divided by the standard deviation. A problem with this is that the distribution of your noise changes to a non-central t distribution. So this would require a modification to the bootstrap method that we've used. And a long-term goal is to use this method to localize peaks. So commonly in an fMRI report, we only report on the peak activations. So what we would want to do is use this method, but that would require a variable threshold depending on the cluster you were looking at. So as a summary, today I've shown why null hypothesis methods become insufficient for population neuroimaging because they find activation over almost the entire brain, and also introduce the contour inference method that we've looked at specifically to infer on non-zero effects. So on this slide, I've just done a little montage showing use of the method over a different number of subjects. And what we see with the tightening of the confidence sets is that not only can these confidence sets give you spatial precision about where activation has occurred, but also the importance of having large enough statistical power to make inference at any sort of confidence. Okay, thank you.